Alright, hello everyone, and welcome. This is the Scholars and Honors video that goes over ionic bonding. I will, as always, have a moment where I say, hey, this is all I'm expecting for Scholars, and then I will go into just some things that I'm only going over with the Honors class for now. And as you can see from my outdated prequel memes, we're going to be talking a lot about ionic bonds, something like lithium, valence electrons, and yeah, you can laugh at my wonderful sense of humor, stale prequel memes, or you could not and just make fun of me for being chuggy. It's alright. So where we're going to start with, we're going to go over valence electrons just really quick, just how to get them. I've explained, multiple times in our past quiz where they come from, so I'm just going to show you the easy method, but you should, for a test, expect to tell me where they come from. I'll go over the octet rule. I will go over basic ionic compounds. I will go over chemical formulas, make things a little bit more complicated. I will go over how to name something, and then I will go over metal ions. So we're talking these elements in the middle here. I will go over them and how to make an ionic compound with them. And that's all for Scholars. For Honors, I'm going to discuss polyatomic ions, and also I'm going to expect a little bit more with these metals here, especially in the way of electron configuration. Alright, so let's dive right into it. Our first is our valence electrons, which I'm going to call VE. And valence electrons are electrons that bond, basically. Electrons that bond. And most of the time, these are going to be from either s or p orbitals in the same period as the element. And I'm using this definition to get away from the rings definition and really just to showcase here. So for example, if we take sodium right here, this is our 3s orbital. So sodium will only have 3s1, and it will be its only valence electron. Once we get to phosphorus over here, we will have 3s2, 3p3. This means that we have 2 plus 3 is 5 valence electrons. But if we go down a row, or we go down to period 4, arsenic is going to have just the orbitals in here, and 4p. Arsenic is going to have 4s2, 3d10, 4p3. Because we are in period 4, we do not count the 3d10 as valence electrons. We only take from 4s and 4p. We take these two, and that's how we get to 5 valence electrons. Easiest way to kind of do that, that is our definition. I said I wasn't going to, but I did. Easiest way to do that. We're not going to worry about this for now, in the middle here, or down here. We're never going to worry about down here. Group 1 and group 2 is how many valence electrons there are. There's 1 valence electron in group 1, 2 in group 2. We're going to skip all of this for now. When we get to group 13, get rid of the 1. Get rid of the 1. Get rid of these 1s. That will tell you how many valence electrons each element in the group has. So boron, 1, 2, 3. Nitrogen over here, group 15, 1, 2, 3, 4, 5. Okay? And I've also kind of just done the Lewis dot structures. I think these are pretty easy. That's just based off of how many valence electrons you have. Fluorine has 7. 1, 2, 3, 4, 5, 6, 7. I know that one's a little out there. Okay? So I will be using Lewis dot structures to really make this a little bit easier. It's a good representation of what's going to be going on, and it will absolutely help us in our next chapter. Okay? So the first thing we're going to go over is the octet rule. So I want to start off by just showing our sodium. Or let's start with chlorine. No, let's start with fluorine. It's a good one to show. Here's fluorine. Fluorine has a electron configuration like this. And I'm just going to show these valence electrons. I don't care about the other ones. Here's our 2s and our 2p. 1, 2, 3, 4, 5, 6, 7. Okay? So, to add another electron here, if we were to complete and get to 2p6, this gives us an immense amount of stability. Having this full shell, or this full orbital, if we added this, that would be very stable. So atoms, they want to be stable. And the reason they're stable is, I'll get to it briefly now, is basically if you would add another one, it would require a ton of energy. It would require a ton of energy to take them away because there's so many in here. We'll get into this next week. Alright, so just believe me for now when I say this is stable. I keep saying next week, who knows with our schedule. We will get into it this chapter. It's a better way of putting it. So this would be stable. If we added equals stable. If we were to add one more electron in here. Alright, so here is fluorine with its 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. If fluorine gets one more electron, here we have this electron, and it comes into fluorine. Boom, like that. This is now stable. Because it has 8 valence electrons. Okay? Now, when you change the amount of electrons, you are changing the charge of this atom. Fluorine, if we go to our periodic table, is atomic number 9. Which means that there are 9 protons. It also means when there is 0 charge, there would be 9 electrons, which gives us a 0 charge. If we added one more electron, now instead of 9 electrons, we have 10. And our charge is just going to be a positive 9 plus a negative 10, because a proton has a +1. Electron has a -1. And this would give us a -1 charge. The other way that I've been talking about this in class, and I think this might be a little bit easier, I'm not sure. I want to give you both methods so you can choose which is easier for you. Right here, I have added. This is me adding. So I am adding an electron. But I'm using this verbiage, this words, very specifically. We are adding. There's our addition. An electron, which has a -1 charge. We started at 0 charge. So we are starting at 0. I should get rid of this equal sign. We started at 0. We are adding a -1 charge. So our charge is -1. So when we write this, it will look like this. Again, when we have a charge of 1, we don't write it as a 1. Just to show you another example where this happens, when you have x, you don't write x to the first, even though that is correct. When you add a 2, that's when you would start to write it. So you would write something x to the 2 minus instead of x, to the 1 minus. So it's kind of an invisible 1. We see a lot of invisible ones throughout chemistry. We'll see them, even later in this video. So that's fluorine. And I wanted to show our electron configurations to show why having 8, it fills that 2p orbital, and now the entire 2p and 2s electrons are filled, which gives it stability. Now, if we go to sodium, sodium here has 11 electrons, and our electron configuration is 3s1. And I'm going to include some of the neon stuff here. Just basically what we had seen from before. And I'll also include the 3p. 1, 2, 3, 4. I know I'm not supposed to put it in like this. Here is sodium with its 11 electrons. We could also I'll just put the 1s. There you go. So sodium has a single valence electron because it is in period 3. It's in group 1, so we also know it's got 1 valence electron. Now, to get to 8, you could add 1, 2, 3, 4, 5, 6, 7. But to do that requires a lot of energy. Now, we don't want to spend energy on things we do not have to. And again, this is another topic that we will go over in this chapter about energy. We're going to really start about it in our next, like right after our quiz and all of that. We're going to talk a lot about energy. So this is bad. We don't want to spend energy. Instead, we're going to get rid of this electron. We're going to remove it. We're going to say goodbye. Leave. I do not want you. Now, sodium, its highest level of electrons will default to the 2s and the 2p. This is now stable. So having in a Lewis dot structure either 0 or 8 electrons is stable. Because the new valence shell becomes this 2s and the 2p orbital. So this, without its 1 valence electron, would be stable. It's important to note here, again, we started out with 11 electrons, or sorry, 11 protons, I should say. We are subtracting, we are getting rid of, giving this away. We have 10 electrons. So our charge would be 11 plus negative 10, or a positive 1. The other way that I've been really going over this in class, because I think it's easier, we are subtracting. We are getting rid of, losing an electron. So you're starting at a charge of 0, this no charge. You're subtracting a charge of -1. When you subtract a negative, you will get a positive 1 charge. We would say sodium plus. Now sodium plus is stable. Okay? So I want you to do some examples here. Give me what ion will make each of these elements stable. And I'm going to give you the elements. It is up to you to find out how many valence electrons they have and how what ion they will form. So I will do this. And we will do this. Okay, so pause the video. Work on these examples on your own. Again, what you're doing is finding how many valence electrons they have, drawing them into the Lewis dot structure, and calculating what ion it will form. Alright, so I will go through this. Here is magnesium, our first one. It is in column 2. It is in the second group, 1, 2. So we will get rid of these 2 valence electrons. We started at a charge of 0. We are subtracting 2 electrons. So our charge would be magnesium, the 2 plus charge. Phosphorus, group 15, 5 valence electrons. 4 or 5. Now to get to 8, we could either lose all 5 of these, or we could add 3. I'm going to add 3. I'm going to do it in a different color too, to show you. 1, 2, 3. So we have started at 0. We have added 3 electrons that have a negative charge, we end up with P with a 3 minus charge. Chlorine. Here's chlorine, group 17, 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Well, again, we're going to add another one to get to 8. 0 plus -1 Cl minus. Last example is rubidium. Here is rubidium. It is in group 1, 1 valence electron, which we will get rid of. So we are starting at 0 charge. We are subtracting, removing a negatively charged electron, and our ion will be rubidium plus. Okay? So it's important to know the ions, more so when we really start getting into metals and how they will form and what our formulas will be for those. The big idea behind it is that we're going to be balancing charge. Okay? So let's start with our basic ionic compounds. I'm going to use the most classic example. We're going to use table salt, which is sodium and chlorine. Here is sodium. Here is chlorine. Okay? As a reminder, sodium, this is the explosive metal. Here is chlorine. Chlorine was the poisonous gas. Okay? I'm giving that to you for reference to show you that when you have these valence electrons that are not full, you will get completely different properties than when they are full. So we're going to give this 1 valence electron to chlorine instead of just popping out of nowhere. Like that. Now, we have sodium with a plus charge and chlorine with a minus charge. Sodium plus, not explosive. Chlorine minus, not poisonous. When we talk about stability, we talk about, is it able to transfer electrons? Sodium is explosive because it really wants to get rid of that 1 electron. In some cases, getting rid of that electron, and we'll get into energy, but that's what releases the energy. That's what makes it explode. It's because its explosion is it getting rid of that electron to become more stable. This is a positive ion. This is a negative ion. So I'm going to use these terms. A cation is a positive ion. An anion is a negative ion. And positive or negative just means the charge. So this cation, it has a positive charge. This sodium plus is a cation. The anion has a -1 charge, so it is an anion. They attract. Opposites attract. I don't have any magnets with me, which is unfortunate, but an opposite will attract. A positive charge is attracted to a negative charge, and they will connect in what we will call an ionic bond. Bonds are ways that different elements connect to one another. It is called ionic because we are dealing with 2 ions. They are very descriptive with this name. Okay? It's important to note that when you have something like this, this is what we would call our ionic compound. Sodium and chlorine as these ions that are connected. But they are 3-dimensional beings. And I could just look up our structure here. And I can go to image here. It will form something like this. It's probably a better way to look at it. They will form 3-dimensional crystals with one another. I'll open this image up. this forms a three-dimensional crystal. And we'll talk about this crystal and kind of what it means. But note that, this atom in the middle is connected to 1, 2, 3, 4, 5, 6 different atoms. I'm not going to go into the different structure. We'll actually, and I'll show you. I'm not going to expect you to know it, but we will see that these structures can get really complicated pretty fast. All right. But it's important to note that we only talk about this in the lowest ratio of atoms. We have 1 sodium to 1 chlorine. Okay, if you were to count this up, you would have the same amount of sodium and the same amount of chlorine atoms. So we're going to write what is known as a chemical formula. I'm going to go back to here, and I'm going to use a different color for this. A chemical formula. All this tells us is what atoms are in whatever compound we have. In this case, going way, way back to chapter 1, a compound is 2 or more elements bonded together. Okay? So we have 2 or more different elements bonded together. Because they are ions, we call this an ionic compound. Our chemical formula just tells us what is the ratio of atoms in this ionic compound. Now we have 1 sodium, 1 chlorine. The order that we do this in is always cation first and then the anion. So here is NaCl. I said cation, I said anion, and I did not write the charge in. I did not go like this, and I did that very specifically. The reason is, when you have these 2 charges, they will offset each other. They will become not charged while they are together. Our overall charge of this ionic compound, if we take this ion, we have a +1. If we take this ion, we have a -1. If you add these up, you get 0. So when we write it, we will just write it like this. NaCl. Okay? And it's important to note that unless stated otherwise, I'll write this at the top. Unless stated otherwise, so unless I tell you otherwise, I'm going to use IC for this an ionic compound has a charge of 0. That's a 0. It's not hard. It's not easy writing with a pen here, with a mouse. So unless I tell you otherwise, and I say there's a charge on this, assume the ionic compound has a charge of 0. Okay? Alright, so I want to get into another example of something that's a little bit more just, we're getting a little bit more complicated. We're going to do, if we go back here, I'll clear this out. We are going to do the ionic compound between calcium and bromine. Alright? So, calcium, group 2, 2 valence electrons. Bromine, group 17, 7 valence electrons. 1, 2. Bromine. 1, 2, 3, 4, 5, 6, 7. So calcium, we're going to bring 1 of its electrons over here. Now bromine starts at a charge of 0, and we are adding a negatively charged electron, which will give us a charge of -1. This calcium still has a valence electron, and this valence electron is going to, it's going to make it unstable. It's going to want to get to 0, or in this case 8. It's going to want to get rid of its 2 valence electrons to get to a lower full shell. It's a better way of watching my words there. So we're stuck with this 1 valence electron. What we're going to do, we're going to bring in another atom of bromine. Alright, we're going to bring in another atom of bromine that has 7 valence electrons, and we're going to bring our calcium over there. Now this one too will have a -1 charge. Calcium starts at a charge of 0, and it is subtracting, getting rid of 2 valence electrons. It will have a charge of +2, or 2 plus. So we're going to have something that looks like this. Calcium with 2 plus, bromine minus, bromine minus. Alright, and if you add up the charges here, again, we have 2 plus -1. There's an invisible 1 here, don't forget that. Plus -1, this gives us a charge of 0. So our net charge, the overall charge, net meaning overall, will always be 0. Unless I tell you otherwise. When we write out the formula, we always go with our cation, which is our positively charged ion, Ca. We're going to put in our anion. However, we have 2 copies of the bromine. So we use a subscript, which is a small number underneath, to write this in. This will become CaBr2. Okay? What I want you to do now, I want you to do the example. I'm going to go to the periodic table. I'm going to clear this. What will form between potassium and oxygen? So I hope you pause the video, try this out on your own, and I will come back and to the answer. Okay, so here's your unpausing this video after you've done this example. Potassium, group 1, 1 valence electron. Oxygen, group 16, 6 valence electrons. Okay, with our 1. Oxygen, 1, 2, 3, 4, 5, 6. So, potassium is going to give its 1 valence electron to oxygen like this. Potassium, run out of valence electrons. It's happy now. Its charge is going to be 0. We are subtracting 1 electron to get to a +1 charge. We'll get K+. Oxygen only has 7 valence electrons. It's still missing another one. We're going to bring in another K, and it will give its electron to oxygen. So we get another K+. Oxygen starts at 0. It is gaining 2 negative electrons to get a -2 charge, and they will connect like this. Alright, so our formula, we always put our cation first, which is our K, and then we put our anion. We get Ko, but we have 2 of these Ks. We have to put in our subscript before the oxygen. This tells us there are 2 copies, 2 atoms of potassium, and only 1 atom of oxygen. This is where that invisible 1 comes here. We kind of assume that there's just 1 atom of oxygen. We don't write it in. So just fun. I did say I would bring this forward. This is the potassium and the oxygen, like how it would fill up. Where did my marker go? Hold on. Go over here. Alright, it's not loading, but these red atoms are oxygen, and the purple is potassium, and you can see that there's a lot more of the potassium than the oxygen. Alright, so just a quick aside, it gets even more complicated than that. I'm gonna pause and I'm gonna just show you one more weird, wacky example. So you can get into weird stuff like this, and it gets even more complicated when you start adding polyatomic ions. I mean, like, some of these structures are just, yeah, they get really, really kind of wacky. Alright, so just a quick heads up about why I'm not going into that. Alright, so here is our example. What I want to do, I can give you other examples. You know, I have done that throughout. What I'd like to do is to give you one example with, where am I looking for, the eraser? When things get a little bit more, I guess, complicated, when we start adding things like aluminum and oxygen. So this is actually the example that I just showed you. We go to our periodic table. Oxygen has 6 valence electrons. Aluminum, group 13, will have 3. So we're going to come back to here. 1, 2, 3. Oxygen. I'm just going to redo this. Aluminum, 1, 2, 3. Oxygen, 1, 2, 3, 4, 5, 6. Okay, so we start to try to fill this up, and we're going to realize it really doesn't work easily. So we take this aluminum, this electron, and this electron. So now this oxygen is happy. Give it a happy mark. But aluminum still has one more. So we bring in another oxygen. And this aluminum is going to give it to this oxygen. But this aluminum is now happy. But this oxygen is still sad. It has 7 valence electrons. So we're going to bring in another aluminum. It will give one of its valence electrons to this oxygen. And I'll draw these in. So this is now happy. But then this aluminum still has 2 more valence electrons, so it's not happy yet. So we bring in a third oxygen. Now finally our numbers start to work out. And all of our atoms have 8 valence electrons. So when we get a formula like this, we start out with our cation. This aluminum, it starts at a charge of 0. It is losing, subtracting, -3 to become a 3+. Okay? So aluminum is our cation. Oxygen is our anion. How many atoms of aluminum do we have? We have 2 of them. How many atoms of oxygen do we have? We have 3 of them. And you will get something that looks like this. Alright, so the way that I would, the easiest way to do this is to think about this from a standpoint of charge. Instead of, we could, do something like this. But to think about it in the concept of charge. Aluminum has a +3 charge. Oxygen has a -2 charge. Every single ionic compound, unless I tell you otherwise, will have a charge of 0. We need to get to 0. So we can take the least, what's the math term? The lowest common denominator, I think that is. Lowest common multiple. That's the word I'm looking for. Alright. Lowest common multiple. From 3 and 2, we can multiply them together. We get to 6. So to get from 3 to 6, we have to multiply by 2. To get from -2 to -6, we have to multiply by 3. And we see this here. We multiplied by 2, and we have 1, 2. We multiply by 3, 1, 2, 3. And if you notice, +6 and -6, 6 plus -6 equals 0. So we can get how many times, what did you multiply by to get from your charge to the lowest common multiple? And that's how many of that atom you will have. And this will be pretty useful when we get to metals. Okay, so last thing I'm going to do is just quick naming these types of compounds. So to name it, you will take the cation, just the element name. So I should really be writing cation element plus the anion element with the IDE, I-D-E ending. So what does this mean? Oh my goodness. Let's take what we had just done, aluminum and oxygen. The element of aluminum is aluminum. Aluminum. Oxygen. What do I mean by the IDE ending? Here is the element oxygen. You're going to get rid of the ending. With oxygen case, this whole last 4 letters. And you will instead add IDE. So we would take our first 2 letters that are still there, OX, IDE, and we would call this aluminum oxide. Okay? There are only, clear this out, 8 elements that I would ever ask about realistically for endings. So we have nitrogen, which would be nitride. We have phosphorus, which would be phosphide. We have oxygen, which I just said was oxide. Sulfur is sulfide. And then all of these, the halogens, you just replace the N with a D. And it would become fluoride, chloride, bromide, iodide. Okay? So those are the 8 that we're really gonna be talking about when we talk about changing the names. So if we had, just as an example, let's just say we had magnesium Mgi2. We would call this magnesium. You use the name of the element. Magnesium. Instead of iodine, iodide. Alright? That's all there is to naming. So I'm going to continue with metals. And what I mean by metals, I'm finally going to talk about these elements. So, for scholars, what I want you to know is that some of these elements can have they can form different ions. I will tell you which ion it will create, but I want you to know the structure of the ionic compound it will form. So let's take iron, for example. Iron over here, it can form either iron 2+, or it can form iron 3+. Okay? So I would tell you it's iron 2+ or iron 3+. I won't be like, hey, you have to, you have to guess. I'm not gonna do something like that unless, well, maybe. I wouldn't have you just be unsure of what it is. You might have to tell me if it's one or the other. That's something that we could do, and I will probably do other examples of that. But you're not gonna have to, guess which one it is without any other clues to help you to solve it, I should say. So if we take, let's just say iron 2+. So they don't technically have valence electrons, because the valence electrons come from the 4s or the s or the p orbitals. Iron's period 4, so that's why I was using 4s. It gets kind of complicated because some of those electrons come from s orbitals. Some of them, they come from the d orbitals. We don't really consider them valence electrons. So drawing them with Lewis dot structures doesn't really make sense. So this is where that whole charge bit really comes into importance. So let's just say we have iron with a 2+. If we take oxygen has 6 valence electrons, which means that this is where that first bit where I really started to ask you what ion will it form. This is why it's important. Oxygen will form a 2- ion, and oxygen will always form 2- for now. It's possible to change. I always say this. There's always exceptions to chemistry. We're going to keep it simple. We'll always form a 2-. Okay? So, if we have iron with a 2+ and oxygen with a 2-, our charge has to be 0, right? Ionic compounds must have a charge of 0. If we just have one of each, we have a 2+ and a -2, or a 2-, that will equal 0. So our chemical formula is FeO. This works when iron has a 2+ charge. But if we have iron with a 3+ charge, an oxygen with a 2 minus charge, like this. Now we have to do that whole thing where we have to balance to get to a 0 charge. We need to find the least common multiple. So to get the least common multiple would be 6 again. So to get from 3 plus to 6, we have to multiply by 2. So we're going to have 2 iron. To get from a 2 minus to minus 6, you have to multiply by 3. So we will have 3 minus. So each one of these are different forms of iron, but they are still, similar. They are still an ionic compound with iron and oxygen, but in different ratios because iron can have a different amount of charge. You can take away different amounts of electrons. Okay? And when we name these, we're going to use the same conventions. So here is iron, and I'm going to use the oxide. But what we're going to do, we're going to add Roman numerals. The Roman numeral that you will add is the charge of the cation. I'm going to say that again. The Roman numeral that you will put in the name is the charge of the cation. Iron 3 plus has a charge of positive 3. In Roman numerals, you will write 1, 2, 3. Put them in parentheses, and it will be iron, parentheses, 3, Roman numerals, oxide. Over here, iron, or cation has a charge of 2. 1, 2. Oxide. So these are similar. They have the same elements, but they will have different properties. I'm going to pause and I'm going to show you these. So just by looking, here's iron 2 oxide. So this is this one over here. It is this black powder. Iron 3 oxide is red. Now, there's obviously differences in their properties as well, but the color is different. That's a property. There's a reason for that. Alright, we're going to talk about iron oxide. Okay, so the last thing I'm going to do for scholars, I'm just going to review Roman numerals. You might not have learned these, and that's okay. So Roman... Alright, cool. I hit the end record button. So, that's why there's a jump. Roman numerals. Oh my goodness. Roman numerals. This is how Romans, counted before we used Arabic numerals, which we now currently use. So, how it works, and this is all I'm going to expect you to ever possibly know. 1, and this is number 1, uses the letter I. So, I is 1. 2, you add another I, and you connect them like this. 3 has 3 I's like this. 4. 4 is where things get really complicated. I'm going to skip 4, go to 5, because you'll see. 5, we use the letter V. We connect it with bars like this. Now 4, I'm going to come back to it. The way that they write it is basically saying 1 before 5. So it looks like IV. It's 1 before 5. Alright. 6, you start adding I's to the other side like this. And then 7 would be 2 I's. This is all I would ever expect you to know. I'm not gonna... You're not gonna see anything more than this. Okay? So this is just a basic guide on Roman numerals. So this is all for scholars. I am going to have to splice videos together, which I love doing. I just want to go through a few extra things with, I know it's already a long video, with the honors that we're going to go through. Okay? So scholars, done. That's all I'm going to expect from you. We will do more examples, and we'll have our quiz. Alright. So, honors. The first thing, when we get with these metals, and I'm not going to expect us to know, I'm going to use the example of iron again, okay? Iron can have 2 plus, or iron can have 3 plus. And if we look at the electron configuration, I'm going to really just skip, forward. I'll go to the electrons. I'll go to iron. I'll pick up this electron configuration over here. 4s2, 3d6 with the argon bit. Here's our 3d. Oh, alright, we'll just put our 4s down here. 1, 2, 1, 2, 3, 4, 5, 6. So the thing with electron configurations and with any of these elements in this range here, which we call the D block elements. So here is iron, 4s2, 3d6. When you make ions out of these elements, you take from the 4s first, from the s electrons first. So we're going to get rid of these two. So iron with the 2 plus, we have Ar. We don't have any electrons in the 4s, we just have 3d6. If you take away another electron here, and this is why this specific ion works, is because it's stable. Having that half-filled orbital is pretty stable. We have Ar 3d5. Alright, so I will expect you, and I will ask for electron configurations of ions. There are other examples, and where I could ask for an ion of a different type of element, and I am considering, because of all these delays, just doing more practice, and I could ask you that as well, okay? But when it comes to these D blocks, this is what you're going to really need to know. Like, let's take, just for example, copper here, okay? So copper is one of those exceptions. You got to remember copper is one of those exceptions. So copper is Ar. I'm going to use our 4s, so we're going to use copper. Our 3d. This was that exception where we had a full shell before the 4s. So we have 4s1, 3d9. Oh, 10, excuse me. Oops. Alright. So, copper with a copper plus is one of the one of the ions that can form. We would get rid of this 4s electron. Get rid of it. Goodbye. Oh my god. After recording for so long, my brain starts doing great things. Ar 3d10. Alright, now copper can also form a 2 plus, which would take away this electron and give us just 3d9. Now, you might be asking, Mr. Aiden, why you talked about how having this full shell is stability and all that stuff. Why is it getting rid of that stability? It's because d orbitals are dumb. It's really just because of that. When you go in, it'll fill up like this, but when you start to take out, it's gonna start to like fill. It'll get rid of the stability here and put it in there, and then you can get rid of 2 of them. It is dumb. It is complicated. I just am gonna want you to give me this. Okay, that's all I'm gonna ask for. I don't want to. I don't want to, dwell on the why. Because sometimes they make sense and sometimes they really it doesn't. And to explain it would require more than I have the time or you have the experience to go through. Okay? So this is all I would ask you for that. The last thing, I don't want to make this too long, is polyatomic ions. So I will give you an ion list. And I have given you an ion list. And you can use that ion list for a quiz and test, anything. That's a reference sheet. Polyatomic, let me write this. polyatomic ions means more than one element in an ion. Alright, so I will take one example, CO3 2-. This is known as the carbonate ion. So I will give you the names, the charges, all of that stuff. The way of looking at this is you have one big ion, X, that has a -2 charge. Okay? In reality, it is, carbon with oxygens like this. And we'll get into the structure of this, soon. Right? But we're just going to consider it one big, friendly, happy, fun ion. Alright? So let's just say, for example, we were creating sodium carbonate. Sodium has a plus charge. Carbonate has a -2 charge. So we need 2 sodiums to make our charge equal to 0. You could even theoretically be like, hey, if we have a 2- charge here, sodium has a +1 charge here, Na positive, 2- Na, like this. You could do like this, using that X to kind of, as a placeholder. Because now our overall charge, +1, +1, -2, equals 0. So our formula would be Na 2 X. We're going to get rid of this X, Na2, replace it with this whole big thing, CO3. When we name this, you take the cation, you take that element, I'm going to put it at the top here. Here's our element, sodium, and you just, whatever the ion is called, whatever it's called, that's what you use. You don't have to change the endings, you don't have to do any of that. This is the carbonate ion, this is sodium carbonate. Boom, you're done. Alright, I will do one last example. I want you to try it. I'm going to give you this following ion. Alright, so here is the chlorate ion. Alright, this is the chlorate ion. It is a chlorine with 3 oh, why did I just draw a 4th one? With 3 oxygens around it. This whole thing, and we'll go over this notation, I'm just showing how we're going to be learning in our next chapter, has a -1 charge. So we have X with a minus charge. I want you to try to tell me what would the formula and the name of a chlorate ion and magnesium will be. Okay? So I will pause the video and try it. Alright, so magnesium will form 2+. Our chlorate, our X, has a minus, which means we're going to need 2 X's. X minus, 2+. Okay? That will get us to a charge of 0. So we will have magnesium and then 2 of the X's. So what are we going to do with this when we put back in our chlorate? We take our Mg. Now, we're not going to put ClO3 2. We don't have 32 oxygens. Instead, we're going to use parentheses to let us know that we have 2 of this whole thing. We have 2 of this ClO3, of this whole big thing that I'm just pointing to. And this is what our formula would be, and our name would just be magnesium chlorate. Move the camera, finish it off. Magnesium chlorate. Alright, And if we just really wanted to look at what this thing would look like, I told you that things get really weird. Do they have it? They don't have it. Yeah, it'll get something like this with different atoms. It gets, yeah. This is why, you know, this is even more complicated. It starts adding really complicated stuff. We're not gonna go through this, okay? We're not gonna do 3 dimensions. Just wanted to show you for fun. So I know this was a long video. And I think I really want to focus on this because I think I'm gonna delay the quiz. I want to do a lot more examples with this to really have us to know this, because I will reference a lot of these different compounds, and I want you to know what they are. Alright, so I'm going to leave us off with just a teaser for our next chapter with this whole polyatomic ions. Yeah, this is why they're fun. Please, I have a whole, like, folder with chemistry memes. Alright, so I hope you've stuck through this whole thing. You know, you can watch it in little bits, but take it easy. Alright?